Hey everyone, welcome to Computer Science Tech Papers Summary. I'm Alex, your guide to the big picture and the fascinating stories behind the code.
And I'm Jordan, here to unpack the precise, brilliant mechanics of how it all works. And today, wow, we're taking a deep dive into a paper that literally paved the way for the digital world we inhabit.
Exactly. Let's start with a thought experiment. Just imagine for a second a world where every phone in your city could only call other phones in your own neighborhood. Bit limiting, right?
Hmm.
Or think about all the amazing apps and services you use every single day. Streaming video, online gaming, video calls with family across the globe. We just kind of take it for granted that they just work.
Yeah, they just magically connect.
But what if all those connections were like separate, isolated islands, each
Yeah.
speaking its own, like, unique language? How would you even begin to bridge those gaps?
That's precisely the monumental challenge our deep dive tackles today. We're going back, way back to 1974, to a truly foundational paper, a protocol for packet network intercommunication by Vinton G. Cerf and Robert E. Kahn.
Whoa, 74, that's early days.
Really early. And this isn't just some dry academic paper, it's practically the original blueprint for how completely distinct computer networks could actually talk to each other. It laid the conceptual groundwork for what we now universally call the internet.
So, like, the DNA of the internet.
You could absolutely say that. What's truly remarkable here is how they envisioned a future that was, well, light years ahead of the technology they actually had at the time.
Okay, so our mission today is to unpack this incredibly dense but
Mhm.
clearly brilliant piece of computer science history. We're going to pull out the crucial insights, the aha moments, and the maybe surprisingly simple, elegant solutions that allow us to connect globally today.
Right.
And you absolutely do not need a computer science degree to get this. Just, bring your curiosity, because the story of how they cracked this nut is pretty compelling on its own.
So let's set the scene a bit. Before Cerf and Kahn came along with this paper, there was already significant, really groundbreaking work being done in designing individual packet switching networks.
Okay, packet switching, like sending data in small chunks,
Right.
not a continuous stream.
Exactly. Think of pioneers like ARPANET in the US,
Yeah.
Cyclades in France, the NPL network in the UK, AloHanet out in Hawaii. These were incredible feats of engineering for their time.
Right.
They allowed computers and terminals within one specific network to share resources and exchange data using a common protocol, their common protocol.
So inside ARPANET, things were great. You could connect to a faraway computer.
Yeah, within ARPANET, you could maybe connect to a mainframe somewhere else on the network, share files, share computing power. That alone was revolutionary for, say, universities or research labs connected to it.
But only within ARPANET.
Precisely. And that's the rub. Here's the really interesting part, the core problem this paper addressed. These individual networks, for all their internal brilliance, were essentially isolated digital islands.
Okay, I like that analogy. Digital islands.
Think about it vividly. Imagine every major city building its own fantastic state-of-the-art highway system, super efficient inside the city limits, multiple lanes, great traffic flow, on-ramps, off-ramps, the works.
It sounds good so far.
But then you realize, wait, there are no roads between these city highway systems. No bridges, no tunnels connecting New York's system to LA's or London's or Tokyo's.
Ah, so you can drive great in your own city, but you can't get to another city.
Exactly. You couldn't drive from New York to Los Angeles without somehow, I don't know, physically lifting your car off one highway system and dropping it onto another. It sounds absurd, but that was the state of networking.
Wow, okay.
The ultimate goal, the true vision, was resource sharing between computers on different networks, not just within the same one. That was the huge missing piece.
And I bet that missing piece wasn't just one problem. There's probably a whole mess of problems.
Oh, absolutely. It brought a whole host of compounded challenges. The paper meticulously highlights 5 key differences between these networks that made interconnection a real nightmare.
Okay, let's break those down. What was number one?
First, addressing. Every single network had its own unique internal way of identifying a receiver, a specific computer, or maybe even a program running on that computer.
Like different phone number formats in different countries.
Exactly like that. So for any global communication to happen for a packet from, say, a computer in London using the NPL network to find its way to a specific server in California on ARPANET, you needed a uniform addressing scheme. something understandable by every network involved.
Without that global phone book, you're just lost.
Totally lost. How would a packet from network A even know how to ask for a computer in network C if they used completely different naming conventions? It couldn't.
Okay, addressing, that's big. What else?
Second challenge, packet size. Different networks built with different technologies, different hardware, different design ideas. They accepted data packets of different maximum sizes.
Like trying to mail a huge box through a post office that only accepts small envelopes.
Precisely. This created a major dilemma. Either everyone had to agree to use the smallest possible packet size across all networks.
Which would be super inefficient for sending lots of data, right? Like
Correct.
sending a novel one letter at a time.
Agonizingly inefficient. Or you needed some complex reformatting procedure whenever data crossed from a network that allowed big packets to one that only took small ones. And that reformatting adds overhead, complexity, potential for errors. It's messy.
Okay, so incompatible addresses, incompatible package sizes. What's number 3?
Number 3, timing and delays. Let's go back to those highway systems. Not only are they disconnected, but maybe one is high-speed autobahn, another is slow city streets with lots of traffic lights.
Right, they operate at different speeds, different rules.
Exactly. The success and performance of a transmission within each network depended on highly variable internal factors. Things like the actual speed of the lines, how much data they could buffer, internal signaling, routing decisions, just the raw physics of signal propagation delay over distance.
So trying to coordinate something across multiple networks, each with its own weird timing.
It becomes incredibly complex. You might have one network that's lightning fast and another that's, well, pretty slow. Ensuring reliable order delivery across that kind of variable landscape was a massive hurdle. How do you make sure piece number 2 doesn't arrive before piece number 1 if they take wildly different paths with different speeds?
Yeah, that sounds tough. Okay, number 4.
Fourth, and this is critical, error handling. Communication within any single network could and did get disrupted. Packets get corrupted by noise, drop due to congestion, equipment fails. Stuff happens.
Right, networks aren't perfect.
Not at all. So to ensure data actually made it reliably from the original source to the final destination, especially when crossing multiple, potentially unreliable networks, you needed robust end-to-end recovery procedures.
End-to-end meaning.
Meaning something that works across the entire journey, not just within one network segment. A single lost packet anywhere along that chain could break the whole message, and there was no universal way to detect that loss and recover from it across network boundaries. Each network might have its own way of handling errors internally, but nothing coordinated between them.
So it's like playing telephone, but if one person in the chain messes up, the whole message is garbled, and nobody at the end knows where it went wrong or how to fix it.
That's a great analogy, and it leads right into the 5th challenge, status and routing. Each network had its own way of handling status info. Like, is that computer even online? How do we route packets to it? How do we detect if a link is down and route around it?
All internal procedures.
All internal, unique procedures. So doing something basic, like just checking if a destination was reachable or dynamically rerouting data if a path failed, required incredibly complex coordination across these totally different systems. It was like trying to get 5 different companies with completely different IT departments and security protocols to seamlessly share sensitive data in real time.
Just chaos, pure chaos.
Pretty much. The paper makes it clear that while individual networks were solving hard problems, connecting dissimilar networks compounded everything. It created entirely new problems. The complexity, both technical and even economic, pushed them towards finding the simplest, most reliable interface possible, because anything more intricate would just collapse under its own weight.
Right, so this sets the stage perfectly. An absolute mess of incompatible, isolated networks. It seems impossible. How do you build a single global system out of that?
Right. This is where Cerf and Kahn come in with this truly elegant, revolutionary idea.
The breakthrough moment.
Exactly. Instead of trying the impossible, making every network understand every other network's unique internal language, like needing a unique translator for every single pair of languages in the world.
Which would just scale terribly.
Terribly. Unmanageably. Instead, they propose something radical. A universal lingua franca just for inter-network communication. A single common language that all networks could use, or at least understand at the border, to talk to each other.
The Esperanto of networks.
Kind of. That was the philosophical leap. And they gave a special name to the component, the interface, performing this crucial translation function, the gateway.
The gateway, okay.
The paper explicitly says its role is to deal primarily with passing data between networks that use different packet switching strategies. notice the wording, passing data between networks. It's not trying to fix or change the internal workings of network A or network B.
It's just managing the border crossing.
Precisely. It's focused solely on the act of getting data between them, translating the envelope or the address label as needed, but crucially without messing with the letter inside.
So let's visualize that. We've got network A, network B, network C, like 3 countries.
Yep.
And connecting them are these gateways, let's say gateway M between A and B, and gateway M between B and C.
Perfect.
When my data wants to go from A to C, it goes through A, hits gateway M.
Which is like the customs and translation office at the border of A and B?
It gets processed there, maybe repackaged somehow, then travels through B to gateway N.
The border crossing between B and C, same process.
And finally enters C to reach its destination. So these gateways are the critical points, the translators at the borders.
Exactly. They're the border patrol, the currency exchange, the language translation service, all rolled into one for data packets. But, and this is critical, that they don't care about the content of your message, just how it's packaged for the next leg of the journey.
Okay, and that leads to a really important point you mentioned. The gateway's role is limited, but smart.
Very limited, deliberately so. The gateway does not try to understand or transform what the paper calls the host or process level protocols.
Meaning, like, the specific language my web browser uses to talk to a web server. Or my email client.
Exactly. The way your specific applications communicate. Trying to make the gateway understand all of those would be, as the paper puts it, unbounded. Think about it, there's a potentially infinite number of ways applications might want to talk now and in the future.
Yeah, the gateway can't be expected to know every single application protocol forever.
It's just not feasible or scalable. Imagine if the border guard had to not only check your passport, but also read, understand, and maybe rewrite every book and letter in your luggage into the local language. Impossible.
Right.
So instead, the gateway focuses purely on the lower level stuff. Packet switching, making sure the data packet can physically traverse the next network. The paper clearly argues that for effective communication, compatible host and process level protocols must be developed. That common understanding needs to happen above the gateway at the application or host level.
Okay, so this is the heart of it. To avoid every computer needing to learn like a million different network protocols.
A potentially unbounded number, as they say.
Right. They proposed a single shared protocol, a common language, to be used between computers or processes in different networks.
Yes. The applications on the communicating computers speak this universal language to each other, regardless of the underlying networks they happen to be sitting on.
And the gateway's job is just to make that possible by handling the translation of the network-specific packaging, the packet formats. It makes the underlying network chaos just disappear from the application's point of view.
It abstracts away the complexity. It's the silent hero in the middle, enabling this universal conversation.
Okay, so if the gateway is the translator, what's it translating? What's this common language packaged in?
The brilliance lies in the standard format they define for packets moving between networks. They called it the internetwork packet format. And crucially, an internetwork header is added to every packet by the source computer, the original sender.
So the sender prepares it for the whole journey.
Yes. This ensures that vital information is uniformly available, in a standard format, to any gateway that packet might encounter along its path.
And what's in this magic header, this universal passport for data?
Several key fields, designed specifically to solve those problems we discussed. First, and maybe most fundamental, source and destination addresses.
The global address book.
Exactly. Uniform, unique identifiers for every computer or host in what they imagined as the composite network, the network of networks, one universal directory.
No more local phone books. Got it. What else?
Then you have a sequence number and byte count. These are crucial for putting packets back together in the right order at the destination, especially if they get fragmented or arrive jumbled up. They also help gateways spot certain kinds of errors.
Okay, sequence numbers for order.
There's also a flag field. Think of this as a set of little switches, just single bits that convey specific control information. We'll dive into what those flags do later, but they signal things like end of message or synchronized connection, very important little signals.
Flags for control signals.
Yeah.
Makes sense.
Then, of course, the bulk of the packet is the text field. That's the actual data you're trying to send, the content of your email or the video frame.
The payload.
The payload, exactly. And finally, there's a trailing checksum. Think of this as a mathematical fingerprint calculated over the data and the header information.
To check for errors.
Yes, but specifically for end-to-end verification by the destination computer. Here's a key point. The gateway doesn't modify the text payload, and it doesn't recalculate this end-to-end checksum.
Why not?
Because the gateway's job is just reliable forwarding between networks. Verifying the integrity of the entire message across the entire journey is the responsibility of the endpoints, the sender, and the receiver. The gateway just ensures the packet gets to the next network. It doesn't vouch for the pristine condition of the original message content across multiple hops.
So the gateway is really just focused on that envelope, not the letter inside. It passes the checksum along, but doesn't check it itself.
Precisely, it maintains that clean separation of concerns.
Okay, let's trace a packet's journey again, using our map. Network A, B, C, gateways M and N, process X and A wants to send data to process Y and C.
Right, so process X creates the data. Its host computer packages it into one or more internetwork packets, adding that standard header with the source X and destination Y, addresses, sequence numbers, etc.
And it sends it into network A.
Network A uses its internal protocols to route that packet towards the border, towards gateway M.
Okay, now it hits gateway M, the crossing between A and B. What happens there?
At gateway M, the packet is, as the paper says, reformatted to meet the requirements of network B.
Reformatting the envelope, not the letter.
Exactly. Maybe network B uses smaller physical packets or needs a different local address format on the outside. The gateway takes the inner network packet, wraps it in whatever network B needs for internal transport, and sends it on its way into network B.
And it also does accounting.
Right.
Tracks the traffic flow.
Yes, that's an important function. Gateways would likely handle accounting for traffic exchanged between the networks they connect. Network A needs to know how much traffic it sent to B, and vice versa, perhaps for billing or capacity planning.
Makes sense. Okay, so the packet, now wearing its network B envelope, travels across network B.
Until it reaches gateway N, the border crossing between network B and network C.
And same thing happens again.
Same process. Gateway N reformats the packet as needed for network C, does the accounting between B and C, and sends the packet into network C.
And finally, network C uses its internal routing to deliver the packet to the host computer where process Y lives.
And that host computer receives the packet, strips off any local network C headers, looks at the inner network header, sees it's for process Y, checks the sequence number, checksum, and delivers the data to the waiting application.
Wow. It sounds complicated, but also really logical when you break it down. The gateway is just this essential translator at each border.
Exactly. A series of necessary translators, each ensuring the packet conforms to the next network's rules without altering that core internetwork message inside. It's a chain of translation.
And you mentioned something interesting, local variations. Individual networks might add their own headers.
Yes, the paper acknowledges this. Think of the standard internetwork packet as a standard shipping container. It has all the essential info on it for international travel.
Okay.
But when that container enters, say, the internal rail system of a specific country network, that rail system might add its own local tracking tag or manifest to the outside of the container for its own internal logistics.
Without opening the container or changing the international label.
Right. This illustrates the concept of embedding or encapsulating the standard internetwork packet within a network's own native format. The core internetwork packet remains untouched, but the specific network can add its own instructions around it for its internal switches.
So it lets networks maintain their own internal ways of doing things while still participating in the bigger internetwork conversation.
Clever. Very clever. It allows autonomy while enabling interoperability. It's a really flexible design.
Okay, but now we hit that problem we mentioned earlier, packet sizes. What if Network A sends this huge packet perfectly fine for its own system, but Gateway M knows that Network B can only handle tiny ones?
Yeah, the moving truck trying to get onto the road with only space for compact cars. The paper explicitly says each network may accept data of different maximum size. This isn't an edge case, it's an expected reality. You have to solve this.
And the solution is?
Fragmentation. It's a core concept. The gateway, facing this size mismatch, might be forced to split a packet into two or more smaller packets.
It chops up the big packet.
Exactly. It takes the original internetwork packet and divides its data payload into smaller pieces, creating multiple new, smaller internetwork packets. Each of these fragments gets its own internetwork header, largely copied from the original, but with adjustments to things like the byte count and flags to indicate it's a fragment.
And crucially, it has to be done so the destination can put it back together.
Right. Absolutely. The fragmentation process must include enough information primarily using those sequence numbers and potentially some offset information or flags so that the final destination host can perfectly reassemble the original packet, even if the fragments arrive out of order. It's like breaking down the moving truck's cargo into numbered boxes for the smaller cars.
And why do this at the gateway?
Hmm.
Why not make the sender figure out the smallest size along the whole path?
Good question. They argue it's most efficient to do it at the gateway because only this gateway, and not the other networks, must be aware of the internal packet size parameters which made the fragmentation necessary.
Okay, so the gateway connecting A and B knows B's size limits,
Yeah.
so it does the chopping. Network A doesn't need to know about B's limit.
Exactly. It keeps that internal network information localized to the border. Imagine if every computer sending data had to know the packet size limits of every potential network its data might cross. That information changes, it's complex, it's unmanageable.
Yeah, that would break scalability immediately.
It-
Localize the problem at the border gateway. Makes sense.
It keeps the system modular and avoids that ripple effect of complexity.
Okay, but here's the part you hinted was really critical. Why not reassemble at the next gateway? If gateway M fragments a packet for network B, why doesn't gateway N put it back together before sending it into network C? Seems logical.
It does seem logical on the surface, but the paper takes a very strong stance against gateway reassembly. They say gateways should not perform this function. And they had some really solid reasons which fundamentally shaped the internet.
Okay, lay them on me. Why is gateway reassembly a bad idea?
First, buffering problems. To reassemble, a gateway would need to store all the fragments of a packet until the last one arrives. What if one fragment is delayed or lost? The gateway has to hold on to the others, using up precious memory, buffer space.
And if lots of packets are being fragmented and waiting.
You could run out of buffer space quickly, leading to gridlock or deadlocks, as they call it. The gateway just gets overwhelmed trying to hold all these partially reassembled packets.
Okay, buffering issues. What else?
Second, forced paths. If gateway N has to reassemble fragments that came through gateway M, then all fragments of that original packet must travel through both M and N.
Oh, it removes routing flexibility. What if there was a better path from B to C that didn't go through N?
Exactly. You couldn't use it for those fragments because they have to meet up at gateway N for reassembly. This restricts the network's ability to dynamically route around congestion or failures. It forces traffic down potentially suboptimal paths.
Right, that's a big downside. Third reason.
Third, increased delay. Simply waiting at an intermediate gateway for all fragments to arrive, then performing the reassembly process, adds latency. It slows down the overall end-to-end delivery time. Why add delay in the middle if you don't have to?
Good point. Any others?
Fourth, they noted it's potentially an incomplete solution. Even if gateway N reassembled the packet, what if network C also had a smaller packet size limit than network B?
Gateway N would just have to fragment it again.
Right. So the intermediate reassembly might have been pointless anyway. You're just potentially adding complexity and delay for no guaranteed benefit.
Okay, so for all those reasons, buffer problems, forced paths, added delay, potentially pointless.
The conclusion was crystal clear. The destination host must be prepared to do this task. The responsibility for reassembly rests entirely with the ultimate recipient, the computer the message was actually intended for.
And that simplifies the gateway's job tremendously. Just translate the envelope and forward, or fragment if needed, but never reassemble.
Exactly. It keeps the network core, the gateways, and the links simpler, faster, and more robust. And it pushes the complexity of reassembly to the edges, to the end hosts, which are generally more equipped to handle it with more memory and processing power.
This sounds like that end-to-end principle you mentioned earlier. Keep the network dumb, make the endpoint smart.
This is a prime example of the end-to-end principle in action, even before the term was widely popularized. It was a radical insight. Don't burden the core network infrastructure with complex application-specific tasks like reassembly. Let the endpoints handle it. This decision was absolutely fundamental to the scalability and resilience of the internet.
Wow, okay. And they even thought about the money side, accounting.
Yeah, interestingly, they suggest that even with fragmentation, the cost to the user shouldn't increase. The idea is, if network B forces fragmentation because it handles smaller packets, it might charge less per packet than network A, which handles larger ones. So while you send more packets, the cost per packet might be lower.
So fragmentation might even decrease the total cost sometimes.
It may actually decrease it, the paper suggests. This creates a neat economic incentive for networks to be efficient and maybe support larger packets, as it could potentially lower user costs and make the network more attractive. aligning technical goals with economic incentives, very forward-thinking.
Okay, we've talked a lot about getting packets across networks, fragmentation, addressing,
Yeah.
but what about the actual applications? The processes running on the computers?
Right, moving up the stack. At the application level, processes, think of your web browser, your email client, a game they want to communicate using messages. These messages can be theoretically unbounded but finite length, could be short, could be very long.
Like sending a whole email or requesting a whole web page.
Exactly. Now, these potentially large messages need to be broken down into smaller chunks suitable for packaging into those internetwork packets we've been discussing. This breakdown happens inside the host computer, performed by a program they call the Transmission Control Program, or TCP.
TCP, we still use that name today.
You certainly do. This paper is where the concept originates. The TCP breaks the application's message into smaller pieces called segments. Think of the message as a book, and the TCP breaks it into chapters, the segments.
And then each segment goes into a packet.
Pretty much. Each segment is then packaged into one or more internetwork packets for transmission across the networks. And the paper specifies that these segments should be made up of an integral number of 8-bit bytes.
Why 8-bit bytes specifically?
Even back in '74, standardizing on 8-bit bytes, octets, was a practical choice for ensuring consistency across different computer architectures. It provided a common unit for data exchange.
So the TCP is doing this chopping into segments. What else does it do?
The TCP is crucial. It handles multiplexing, that's taking segments from different applications or processes running on the same computer and funneling them into the stream of outgoing packets, like a mail sorter gathering letters from different desks to go out in the same mailbag.
Combining streams.
And it handles demultiplexing on the receiving end, taking the incoming stream of packets, figuring out which segment belongs to which application, and delivering it to the correct destination process, like sorting the incoming mail into the right internal mailboxes.
So it's the traffic controller inside the host computer?
Yes, managing multiple conversations simultaneously. It also handles breaking messages into segments, not just because of application message size, but also potentially due to network packet size limits or just to share network resources fairly between different active processes.
Okay, now here's a big decision point the paper mentions. How should the sending TCP format these segments for the receiving TCP? They had two options, case 1 and case 2.
Right, this was a fundamental choice about how segments relate to packets. Case 1 proposed treating all segments destined for the same receiving TCP as just one continuous stream of bytes.
Like just dumping all the chapters of the book into one long scroll.
Sort of. The potential advantage was efficiency. Maybe you could pack multiple small segments into a single internetwork packet, sharing the header overhead.
Well, what's the downside?
The big problem comes with packet loss and reordering, which are common. If packets arrive out of order, or some are missing, how does the receiving TCP parse that continuous byte stream back into meaningful segments? It doesn't know where one segment ends and the next begins if there are gaps or jumbles.
It loses the boundaries. It's like the scroll getting torn and shuffled.
Exactly. You can't reliably figure out, is this segment complete, or where does this piece fit? And it also introduces potential inter-process interference. If multiple applications on the sending host were sharing this single stream to the same destination host, their data could get interleaved in confusing ways. It's just too messy and fragile.
So case 1 sounds problematic. What was case 2?
Case 2, which is the approach they selected, says that each packet should carry information that clearly identifies the specific destination process and provides the necessary sequencing information for that process's message stream. They proposed adding a process header inside the internetwork packet's data field.
So each packet knows exactly which application it's for and where its data fits in that application's message.
Precisely. Each packet becomes a more self-contained unit, representing a distinct, identifiable chunk of a specific message for a specific process.
What are the benefits of that?
Huge benefits. It avoids that inter-process interference because packets are clearly tagged for their recipient application. It allows immediate identification of the recipient process upon arrival. And it dramatically simplifies sequencing and reassembly at the destination, even if packets arrive wildly out of order because each packet carries its own context. I belong to application X, and I am bytes 500 through 599 of its current message.
So each chapter arrives clearly labeled with the book title and page numbers. Much easier to put together.
Much easier, much more robust. It might add a little extra header overhead compared to the theoretical case 1, but the gains in reliability and clarity were deemed far more important. This decision fundamentally influenced how TCP works today.
Okay, so for this to work across different networks, we need that uniform addressing again. But now not just for the host computer, but for the TCPs and these application endpoints.
Absolutely. We need a way to address not just the destination computer, but the specific TCP program running on it, and the specific conversation or endpoint within an application that the data is for. This endpoint concept is what they termed a port.
Ports, like port 80 for web traffic.
Exactly like that. Think of your web browser. It might have multiple tabs open, each talking to a different web server. Each of those distinct conversations needs its own identifier on your machine, so the incoming replies go to the right tab. That identifier is the port number.
So the address needs to specify the network, the host TCP on that network, and the port on that host.
Correct. The paper proposed a hierarchical structure. For TCP addressing, they suggested an address format with two parts. First, an 8-bit network IV. This allows for up to 256 distinct networks.
Which seemed like a lot in 1974, I bet.
Astronomical, probably. And second, a 16-bit TCP identifier within that network. That allows for up to 65,536 unique TCP entities, basically hosts running TCP per network.
Okay, so network ID gets you to the right network, TCP ID gets you to the right computer on that network.
Exactly. The gateway primarily uses the network ID to route the packet across the internetwork to the correct destination network. Once the packet arrives at the destination network, that network's internal mechanisms use the TCP identifier to get it to the right host computer.
And then the port number comes in.
Yes. For port addressing, they needed a way for a TCP on a host to handle multiple simultaneous conversations with different applications, or even the same application doing different things. They suggested 16 bits are sufficient to serve as internetwork port identifiers.
16 bits, that's also 65,536 possible ports per host.
Right. This allows a process to distinguish between multiple message streams. It's that final piece of the address, the specific mailbox number for the application running inside the destination computer. So the full address effectively becomes network plus host plus port.
Wow, that's basically the addressing scheme we still use today with IP addresses and port numbers. Amazing foresight.
It really is. They laid out the fundamental structure for global addressing that proved incredibly scalable and enduring.
Okay, so we have addressing sorted, packets flowing, segments identified, but networks are messy. How do they ensure reliability? Putting the pieces back together correctly.
That's where sequencing becomes absolutely vital. How do you reassemble that message, especially if packets got fragmented and arrived out of order?
Yeah, sounds like a recipe for disaster.
Their solution was elegant. Remember that sequence number in the internetwork header? They defined it very carefully. It's unique within a specific destination port message stream, meaning for a particular conversation between two ports.
Okay, unique per conversation.
And these numbers are monotonic increasing. They always go up. Crucially, they represent the byte position of the first byte of data in that packet relative to the beginning of the entire message stream for that conversation.
So not packet 1, packet 2, packet 3, but byte 0, byte 500, byte 1000?
Exactly. Imagine every single byte in your message stream has its own unique serial number starting from 0. If a packet contains 500 bytes starting at byte 1000, its sequence number is 1000, and its byte count field says 500.
Ah, I see. So even if packets arrive completely shuffled, you know exactly where the data in each packet belongs in the final reconstructed message.
Precisely. The paper states this allows the exact position of the data in the reconstructed message to be determined even when pieces are still missing. You can literally see the gaps and put the arriving pieces into the right place in your buffer based on their byte sequence number.
That's incredibly robust.
What?
Okay, but how does the receiver know when a segment is actually complete or when the entire message is finished, especially with fragmentation?
Good question. That's where those little bits in the flag field come into play. Two flags are particularly important here, ES and EM.
ES and EM, what do they stand for?
ES means end of segment. The sending TCP sets this flag on the last packet that makes up a particular segment it created. This signals to the receiver, okay, the segment defined by the preceding packets is now complete, and you can expect a checksum for the segment to follow.
So it marks the boundary of a segment. And EM?
EM means end of message. The sending TCP sets this flag on the very last packet of the entire message it's trying to send.
Ah, the grand finale signal. That's all, folks.
Pretty much. It tells the receiving TCP, you now have all the pieces of the complete message I intended to send you.
Okay, but what happens to these flags if a gateway fragments a packet? Say, a packet had the EM flag set, but it gets split into two fragments.
Excellent point. The gateways have to handle this carefully. When a gateway fragments a packet, let's say packet A is split into A1 and A12, it copies most of the header, adjusts sequence numbers and byte counts for the fragments. Crucially, if the original packet A had the ES or EM flag set, only the last resulting fragment, A12 in this case, will have that flag set.
So the flags only appear on the very final piece of the original segment or message, even after fragmentation.
Correct. This ensures the destination. TCP doesn't mistakenly think a segment or message is complete just because an intermediate fragment arrived. It waits for the fragment carrying the original flag. This allows the receiver to correctly verify checksums for segments and reliably detect when the full message has arrived, regardless of how it was fragmented en route.
That's some intricate choreography between the hosts and the gateways.
It has to be, to maintain end-to-end integrity despite the complexities in the middle.
Okay, sequencing and flags help put things together. But what about packets that just get lost? Or packets that get duplicated somehow? The paper admits transmissions aren't 100% reliable.
Right. You absolutely need mechanisms for retransmission and duplicate detection. The core idea proposed is timeout and positive acknowledgement, ACK.
How does that work?
The sending TCP sends some packets. It then starts a timer. It expects to receive an acknowledgement ACK packet back from the receiver confirming receipt of that data. The ACK is basically a got it message, often piggybacked on data packets going in the reverse direction. If the sender's timer expires before it receives the expected ACK,
It assumes the packet or the ACK got lost.
correct. It assumes something went wrong and it will retransmit the unacknowledged data.
Simple enough. But wait, if it retransmits, how does the receiver know if the packet arriving now is the original transmission that was just delayed, or the retransmission? Or maybe the original did arrive, the ACK got lost, and now this retransmission is an unwanted duplicate.
Ah, you've hit on a critical problem. Duplicate detection. This is essential. How do you distinguish old, possibly duplicated data from new data? Especially since sequence numbers eventually have to wrap around and be reused.
Yeah, if you just keep counting up, eventually you run out of numbers and start back at zero.
Exactly. Their proposed solution is ingenious. A window strategy.
A window, like a window of time.
More like a window over the sequence numbers. Imagine that long stream of byte sequence numbers for your message. The sender and receiver agree on a window size. Let's call it W.
Okay, a window of W bytes.
The sender is only allowed to send bytes whose sequence numbers fall within its current window, which starts at sequence number L and goes up to L plus W1, without having received an acknowledgement for byte L.
So it can only send a certain amount of data ahead before it has to wait for confirmation.
Exactly. It's like having a credit limit.
Yeah.
You can send up to W bytes on credit, but then you need acknowledgement for the oldest outstanding byte before your credit limit, the window, can slide forward and you can send more.
How does this prevent confusion with duplicates and sequence number wraparound?
The key is in how the window size W relates to the total size of the sequence number space. Let's call it N. They established a rule.
Yeah.
The window W must be less than half the sequence number space.
WN2.
Why less than half? This mathematical constraint ensures that if the receiver gets a packet, it can always unambiguously tell if that packet's sequence number falls within its current expected window, new data, or if it belongs to a previous cycle of sequence numbers, old duplicate data. There's no overlap possible between the valid new window and the old window from the previous cycle if W is less than N2.
Ah, that's clever. It guarantees you can always distinguish between a retransmission of old stuff and genuinely new stuff, even when sequence numbers repeat.
It's a fundamental mechanism for ensuring reliable delivery in the face of loss and duplication. The paper details precise rules for how the sender manages its window, transmitting up to L plus W1, advancing L upon receiving ACKs, and how the receiver manages its window, accepting packets within its window, sending ACKs for the next expected byte L, discarding packets outside the window.
And the receiver might hold on to packets that arrive out of order, but within the window.
Yes, the receiver can optionally buffer packets that arrive out of order but are still within the current valid window, waiting for the missing pieces to fill the gaps. Or it could discard them, relying on the sender's timeout and retransmission. But the key is, it only acknowledges data contiguously from its left window edge.
What are the big benefits of this whole window approach?
Several major benefits. First, it allows for pipelining. The sender can have multiple packets in flight simultaneously up to the window size, which dramatically improves throughput compared to sending one packet and waiting for its ACK before sending the next.
More efficient use of the network.
Much more efficient. Second, it inherently handles reordering because of the sequence numbers. Third, It provides robust duplicate detection. Fourth, the acknowledgement mechanism naturally helps resynchronize the sender and receiver if things get out of whack due to lost packets or ACKs.
And this works even if packets get fragmented by different gateways and take totally different routes.
Yes, because everything is based on those end-to-end byte sequence numbers managed by the TCPs. The gateways just handle fragmentation and forwarding. The TCPs at the ends use the sequence numbers and the window mechanism to ensure the original byte stream is reassembled correctly, reliably, and in order, regardless of the chaos in the middle. It's incredibly robust.
Amazing. Okay, so reliability is covered. What about speed mismatches? What if the sender is way faster than the receiver and just floods it?
Flow control. Another critical piece. You need to prevent a fast sender from overwhelming a slow receiver or intermediate network buffers.
How do they tackle that?
They proposed using the window mechanism itself for flow control. Remember, the receiver sends acknowledgments. They suggested including a suggested window field in the packet sent by the receiver back to the sender.
So the receiver tells the sender how big its window should be.
Exactly. The receiver can dynamically advertise how much data it's currently prepared to receive. If the receiver's buffers are getting full, it can advertise a smaller window size in its ACKs.
And the sender is obligated to respect that smaller window.
Yes, a well-behaved sender should throttle its transmission rate so it doesn't send more data than the receiver's advertised window allows.
What if the sender ignores it? Or the receiver suddenly has no buffer space and advertises a window of 0?
If the receiver advertises a 0 window, the sender should stop sending data, except for maybe small probes to see if the window reopens. If the sender does send data beyond the receiver's advertised window, the receiver is perfectly entitled to just discard those packets.
And discarded packets trigger retransmissions later from the sender.
Exactly, which automatically slows the sender down. The paper calls this flow control mechanism exceedingly powerful and flexible, and notes it avoids tricky synchronization troubles seen in earlier schemes that tried to pre-allocate buffers. It relies heavily on the robust retransmission strategy. If the receiver says stop, the sender should stop. If it doesn't, the receiver just drops the excess, and the sender eventually gets the message via timeouts and retransmissions.
So the window mechanism handles both reliability and flow control. That's elegant.
Very elegant. It combines sequence numbering, acknowledgments, retransmissions, and receiver feedback into a single powerful framework.
Okay, moving towards the bigger picture, the paper challenges the whole idea of a connection, as people understood it then, right? The telephone model.
Yes, this is a fascinating philosophical shift. Back then, especially coming from the circuit-switched world of telephones, a connection usually meant establishing a dedicated physical or logical path between 2 points before communication could start. You dial, the switches set up a circuit, you talk, you hang up, the circuit is torn down.
A fixed path for the duration of the call.
Right. But in this new packet-switched world, data is broken into independent packets. They might take different routes. There is no single dedicated circuit. So Cerf and Kahn asked, does the old concept of connection even make sense here?
What did they propose instead?
They introduced the term association. They defined it carefully as a relationship between 2 or more ports that are in communication or are prepared to communicate without regard to any path.
Without regard to any path. That's key.
It is. 2 ports are associates if an association exists between them. The crucial distinction is this. An association exists simply when both ends, the TCPs or processes, maintain enough state information like sequence numbers, window sizes, port numbers to allow proper, ordered, reliable communication.
So it's about the state held at the endpoints, not about a path through the network.
Precisely. It does not imply a dedicated path exists, nor does it necessarily mean one end knows the real-time condition of the other end, like whether it's temporarily busy or not, only that they share enough context to potentially communicate meaningfully. It's a logical virtual relationship based on shared state.
That's a much more abstract concept than a physical connection.
It is, and it's much better suited to the dynamic, connectionless nature of packet switching.
They also mention connection-free protocols.
Yeah, they contrast their approach with systems like the ARPANET IMPs, the early routers. The IMPs themselves were considered connection-free because they had fixed static addresses. You just sent a packet address to an IMP, and the network routed it. The IMP was always implicitly ready to receive. No setup needed.
But for applications, processes, ports,
Mm-hmm.
They come and go,
Why,
right?
sure.
Attachments aren't static.
Exactly. Port numbers get reused constantly as applications start and stop. So you can't just assume a destination port is always ready. The idea of having some central registry assign unique, permanent, global port numbers to every application instance was dismissed rightly as violating decentralization. You don't want a single bottleneck or control point for all communication setup.
So if there's no central registry and no traditional telephone-style connection setup, how do two TCPs initiate an association? How do they start talking?
This is where a couple more of those flags in the internetwork header become important: SYN and REL.
SYN and REL. Okay.
SYN stands for synchronize. When a process wants to initiate communication with another port, the sending TCP can set the SYN bit in the flag field of the first packet it sends for that new association. This packet also contains the sender's initial sequence number, ISN.
What does the SYN flag tell the receiver?
It signals to the receiving TCP, "Hey, I want to start a new association with this port. Please synchronize your expected sequence number for this conversation with the sequence number I'm sending you now." It's the initial handshake signal establishing the starting point for the sequence numbers.
Okay, so SYN kicks things off. What about REL?
REL stands for release. This flag has a couple of uses. It can be used by a receiver to reject an incoming SYN request. Perhaps the target port doesn't exist or isn't listening. It basically says, "Nope, can't talk."
Like hanging up immediately?
Kind of. REL is also used to terminate an existing association gracefully. When a process is finished sending data, its TCP sends a final packet that might have the ES end of segment and EM end of message flag set, and also the REL flag.
Signaling, I'm done sending and I want to close this association.
Exactly. The receiver, upon getting the REL, should process any remaining data and then send back its own packet with the REL flag set as an acknowledgement. This ensures both sides agree the association is finished before they discard the state information, sequence numbers, etc. It's a two-way confirmation of termination.
So it's a clean teardown preventing loose ends.
That's the goal, a graceful termination.
Were there any tricky parts to this association management? Any potential problems?
Yes, the paper acknowledges some nuances. One issue is premature dissociation. What happens if a sender retransmits an old packet, due to a lost ACK maybe, after the receiver has already received the REL, sent its own REL, and completely deleted all state for that association?
The receiver wouldn't recognize the retransmitted packet. It would look
Yeah.
like junk, or maybe even a mistaken attempt to start a new association if the port number got reused quickly.
Exactly. This is a real problem, known today as the time-wait state issue in TCP. The paper notes this requires solutions like making ports wait for a certain timeout period before being reused to allow any lingering packets from the old association to die out in the network. They didn't fully specify the solution, but they recognized the problem existed.
So even these pioneers knew there were still kinks to work out.
Oh, absolutely. They were laying the foundation, not building the entire finished structure. They also noted that using SYN and REL this way allows for a very simple, one message at a time transactional style, send a SYN plus data packet, get a REL plus reply packet, which was similar to other connectionless request reply schemes popular at the time.
And then there's that fascinating little bit at the end about security, or maybe privacy.
Yes, this is a really interesting speculative corner moment in the paper. They muse about what would happen if the communicating processes could change their port numbers, external addresses, pseudo-randomly for each message, using a sequence known only to them.
So every message looks like it's coming from or going to a different random port.
Right. From the perspective of someone monitoring the network traffic, each message would appear to be part of a completely different, unrelated association. It would make it much harder for a third party to track the flow of a single conversation or link messages together.
Wow, that's like built-in obfuscation. Thinking about traffic analysis countermeasures way back in 1974.
It's a remarkable glimpse into early thinking about network security and privacy, long before these became mainstream concerns. It shows how deeply they were considering the implications of their design, not just the mechanics.
Okay, so let's try and wrap this up. What's the big summary of what this protocol achieved?
Well, the paper concludes by summarizing its fundamental features. The protocol they designed supports variations in network packet sizes, crucially through fragmentation at gateways and reassembly at the destination host. It handles inevitable transmission failures using timeout, positive acknowledgement, retransmission, and that clever window-based duplicate detection. It provides robust sequencing using byte-level sequence numbers, ensuring correct message reassembly. It includes flexible flow control, allowing receivers to regulate sender speed using the window mechanism. It enables the dynamic creation and destruction of these logical process-to-process associations, moving beyond rigid connections. And importantly, they believed it was implementable by hosts of widely varying capacity, from big mainframes down to smaller mini-computers, making it potentially universal.
There's a heck of a list. They really tackled all those initial problems we talked about.
They laid out a comprehensive, coherent solution to the incredibly complex problem of internetworking dissimilar packet networks.
And they knew it wasn't finished, right? They mentioned next steps. Yes, very clearly. Writing in 1974, they stressed that the next important step is to produce a detailed specification of the protocol so that some initial experiments with it can be performed. They knew theory needed practice.
They needed to build it and test it.
Exactly. They specifically called out the need to empirically determine key operational parameters through real-world testing. Things like, how often do packets actually arrive out of order in typical networks? What are the realistic delays between sending a segment and getting an acknowledgement back? And based on those delays, what are appropriate values for the retransmission timeouts? Too short, and you retransmit needlessly. Too long, and recovery is slow.
So they were setting the stage for the next phase of research and development. Get the specs right, build prototypes, measure, refine.
Precisely. It shows that perfect blend of brilliant conceptual design and practical engineering mindset. They didn't just drop the theory, they outlined the path to implementation.
And they acknowledged others too, right? This wasn't done in a vacuum. Absolutely. They give explicit credit and acknowledge critical input from other giants of early networking. People like Bob Metcalfe, who co-invented Ethernet soon after, folks involved with the NPL network in the UK, like Roger Scantlebury and Donald Davies, Dave Walden from BBN, who worked on ARPANET IMPs, Hubert Zimmermann and Louis Pouzin from the French Cyclades network, which had similar ideas, Steve Crocker, another key ARPANET figure.
It really underscores that the internet wasn't invented by one or two people, but emerged from this incredible collaborative international research community.
Definitely. It was a process of building on each other's ideas, sharing insights, debating approaches. This paper was a monumental step, synthesizing many concepts, but it stood on the shoulders of giants and collaborated with contemporaries.
So reflecting on all this, what we've just unpacked, it's really more than just an old academic paper.
Oh, much more. It's the conceptual bedrock. It's the blueprint that allowed those disparate, isolated networks of the 1970s to eventually evolve and connect, forming the single, interconnected global internet that underpins, well, almost everything we do today.
The ideas seem so fundamental now, but they were revolutionary then. Gateways acting as translators, uniform global addressing, fragmenting packets but reassembling only at the destination, end-to-end reliability with sequence numbers and Windows flow control, these abstract associations.
They were paradigm-shifting ideas. They fundamentally changed how people thought about connecting computers and networks.
And here's a final thought to leave people with. Consider that the core principles laid out in this 1974 paper, nearly 50 years ago, are still fundamentally how our digital world operates. TCP/IP, the protocols that run the internet today, are direct descendants of the ideas in this paper.
It's incredible longevity. Every time you send an email, stream a video, join a video call, browse the web, you are directly benefiting from the foresight and the brilliant, elegant problem-solving of Cerf and Kahn and their collaborators.
What if they hadn't cracked this nut? What if they hadn't figured out how to bridge these digital islands? What would our world look like today? Would we have a fragmented internet? Multiple competing, incompatible internets? Or maybe no global internet at all?
It's impossible to know for sure, but it certainly wouldn't look like the seamlessly interconnected world we have now. This paper didn't just propose a technical solution, it genuinely sparked a revolution in communication that continues to shape our reality every single day.
An amazing piece of history, and still so relevant. If this deep dive has sparked your curiosity about how the internet really works under the hood, there's so much more history and technical detail to explore. We really encourage you to seek out more about these early pioneers and the incredible challenges they overcame. Thanks for diving deep with us today on Computer Science Tech Paper Summary.
See you next time.